Allora. Good afternoon and welcome everyone to this sixth seminar of the PRIMO Talk series. Today I have the pleasure to introduce Alessandro Benfenati as a speaker of this session. He got his PhD at the University of Ferrara, and then he moved to France for a few years where he was a postdoc at the University of Paris-Est, collaborating also with Jean-Christophe Pesquet. And currently he is a researcher at the University of Milano. His research activity mainly concerns optimization methods with application to different areas like image restoration, machine learning, and signal processing on graphs. Today is going to give a talk on matrix optimization, proximal approaches, and majorization minimization strategies. So please, Alessandro, the screen is yours.
Okay, thanks, Serena, also for the nice introduction. Today I want to present my work, my joint work with Émilie Chosnoux and Jean-Christophe Pesquet, work that we've done during my French period abroad. This research is about matrix optimization, and we adopt proximal approaches, and moreover, we develop new functionals that have to be minimized with majorization and minimization strategies. A brief outline of my talk, I will give a little introduction, mainly about notations and so on, to make more clear my presentation. Then I will talk about spectral functions and the Douglas-Rushford algorithm that we use to solve a particular instance of matrix optimization problems. Then I will explain how we derived a non-convex functional to solve such problems. This functional will include information about the noise affecting the given data and how we solve it with an MM approach, a majorization minimization approach. Finally, I present numerical experiments, both on synthetic and real-world datasets, and some conclusion about this work. So, we all know that there are a lot of problems in real life in a very wide range of scientific areas that needs to solve such problems when we have to minimize a Bregman distance of a function f between c and y, plus a regularization functional. This term y is the given data, and the Bregman distance is recalled to be this formulation here, where t is the subdifferential, is the subgradient of the function f computed in y, the given data. We have a very classical example about this kind of problem, is the graphical lasso model, where the function f is simply the minus log det of the matrix of a real symmetric matrix C, and the regularization function G is simply the L1 component-wise norm. It is the sum of the absolute value of the elements of the matrix. This framework is exactly one particular instance of this problem. But we have a big problem, which is that if there are some noise that affects the data, the given data y in the previous formulation, G-lasso models do not take into account this information inside the functional. So we try to adopt two different approaches. The first one is to decouple the regularization function G in two terms, G0 and G1, which the first one is a spectral function, and the second one will be a classical regularization function which acts on the entire matrix, while the second approach is to develop a new fidelity function which includes this information on the functional. The first one is solved by adapting the Douglas-Rushford proximal minimization approach to this problem, while the second, since as I anticipated in the introduction, the new function is not convex, we need some methods that allows to solve non-convex optimization problems, And then we try to use the majorization minimization approaches. Hereafter, I will denote majorization minimization approach with methods. Okay. So if we expand the definition of the Bregman distance, we will have such kind of optimization problem, which is the minimization of f plus or minus, depending on the function, of a trace term plus the regularization function. Let me spend some words about spectral functions. Just a very quick introduction, because I'm pretty sure that everyone knows here what is a spectral function. A function f defined on the space of symmetric matrices is called a spectral if and only if it is just a function on any permutation of its eigenvalues here, where P is a permutation matrix and D is the vector of eigenvalues of the function. Classical examples are the G-Lasso function, the minus log that, the very well-known Frobenius norm, and the negative von Neumann entropy. This kind of function is mainly used in quantum mechanics. And we will spend some words about this in the forthcoming. So for the moment, let's consider the problem, the minimization problem, where we have just the function f, the trace term, and the spectral function G0. Let's discard for the moment the non-spectral function G1. So f and g are just function of the eigenvalues of the argument. We proved this theorem, which I call theorem 1, then that states to solve such kind of problems, we just need to compute the solution as this formula says, where ut is the orthogonal matrix coming from the eigenvalue decomposition of the given data t, and d is the vector of the solution vector to this kind of problem, which involves just the spectral counterparts of the function f and g, provided that this function is just coercive. Note that just phi must be in gamma 0, the space of convex, proper, and lower semi-continuous functions, and the domain of the two spectral counterparts must have a non-empty intersection. So let's come back to, for the moment, for the general formulation, where we have a regularization function which has two terms, G0, which is a spectral function, and G1, which acts on the entire matrix C. You can think as G1 as the L1 component-wise norm, as the golden example that we already seen. Then if we write down the entire functional, we can regroup the spectral parts on one term, H0, and the non-spectral parts in another term, H1. Let's see, moreover, that this allows us to see that when H1 is equal to 0, we have a sort of Bregman proximal operator, which has this formulation. So we have to minimize the G0 function plus the Bregman distance of f. I called it a Bregman-like proximal operator because if you substitute with the Bregman distance with the normal square Frobenius norm, you obtain the classical proximity operator. Then, as an offspring of the previous theorem, we proved this corollary, these results, that once you have such a formulation where G0 and f are spectral functions, you can find the solution to this problem directly using this formula. So you compute the eigendecomposition of the given data y, and then the solution is given by this matrix, where this part in the diagonal matrix is just a proximity operator of psi using the Bregman distance with respect phi of the given data. Why this result is important? Actually, it extends very well-known results about the same kind of problem, but where the Bregman distance here is actually the Frobenius square norm. So we developed a more general framework And moreover, and more important, the previous theorem does not require any convexity assumption on the function G0. So we extended the results also for non-convex function, okay? Then let's come back to the more general formulation where we decouple the regularization function G in two different terms, G0, spectral one, and G1, which acts on the entire matrix. Have in mind always the L1 component-wise norm, okay? Such kind of problems can be solved using the Douglas-Rushford algorithm, whose formulation is given here in these two lines, where in this case the proximity operator is given by this formula, okay? One has to select usually G1 in a clever way in order to have a very simple formulation for the proximity operators of H1, okay? And moreover, the computation of the proximity operator in the first step here can be loaded only on the eigenvalues of the input CK. Indeed, you can compute the eigenvalue decomposition of the argument. This linear term comes from this trace term. If you do some little algebra on this problem, you can recognize from which part this comes from. So you get the eigenvalues. You compute the proximity operators of the eigenvalues using the spectral function, and then come back to the matrix space using the orthogonal matrices coming from the eigen decomposition here. Okay. Then let me present some results that we computed for three different spectral functions. The first one being the Frobenius norm, which is 1/2 times the square Frobenius norm. Indeed, this falls into our formulation because if we compute the Bregmann distance of C and Y when F is the Frobenius norm, we just obtain this part, 1/2 C square minus trace term, which is exactly the framework that we've seen so far. And moreover, by the definition, we can recover that since the Frobenius norm is just the L2 norm of the eigenvalues, the square Frobenius norm is the sum of the square of the eigenvalues. Then everything is in our framework, and then we can give this frightening table of proximity operators when F is the Frobenius norm. So phi here is just the sum of the square of the eigenvalues. And here on the left of this table, we have different choices for G0. For example, the nuclear norm, the Frobenius norm. We introduced also the Schatten-P penalty, the inverse Schatten-P penalty, which is the Schatten-P function computed on the inverse of the matrix. And moreover, we included also some non-convex functional because as we've seen, there are some results that allows us to compute the proximity operators also for non-convex functionals. So we have here on your right the explicit expression for proximity operators with such choices. Moreover, we can use the generalized orthogonal decompositions to compute the explicit expression for proximity operators also for non-integers exponents of the Schatten-P penalty. For example, we computed these formulas for P equal to 3/2 and P equal to 4/3. Let's move on to the logarithm determinant, which is very useful in graph estimation problems. Again, a very quick computation shows that we are again in the framework that we presented so far. And moreover, the log det is a spectral function, and it is equivalent to the negative Berg entropy of the eigenvalues, as you can see here. Okay. We proceeded again to compute some explicit formulations for proximity operators when F is the log det coupled with G0 as seen in this table. We extended also these results when G0 takes into account also pre-multiplication and post-multiplication by an invertible matrix W. And last but not least, the negative von Neumann entropy, which reads as the trace of C log C, where here log C is the logarithm defined on matrices. Again, we can compute the Bregmann distance that falls again in our framework, and we show that the negative von Neumann entropy is the Shannon entropy of the eigenvalues of the matrix. There is this parallel between the matrix function and real functions. We computed again a table collecting some results about the proximity operators. In this case, since the function becomes a little bit more complicated, we have explicit formulations, but they involve the W Lambert function. So in order to compute the solution, we still need numerical implementation of this function. Okay, so I told you about the Douglas-Rashford implementation approach to solve such problems, but now it's time to introduce the real novelty of our work. We encountered in our studies this kind of model where A is a matrix, even rectangular, S and E are multi-valued random variables following Gaussian distributions, which are also independent. And then one can be interested in finding the true covariance matrix of this data. This kind of model arises in machine learning problems in the context of relevant vector machines, which are similar to support vector machines studied in the past. Firstly, on one hand, one can compute the empirical covariance matrix using the very well-known formula, but it is actually a rough approximation of sigma, the true covariance matrix. And moreover, when the covariance matrix is sparse, the empirical one is not sparse at all, usually. So we developed this new functional f plus t of s of c plus deregularization, which again is decoupled in spectral term and non-spectral term. F is a sort, is an offspring of the classical log det determinant, while this tau t of s is this trace term, which looks quite ugly. And indeed it is ugly because it's not convex, it's a concave term. Then we have a convex function, f plus g0 plus g1, plus a trace term which is concave, leading us to have a non-convex functional. Then we resort to use the maximization and minimization approach, which I'd like to depict here very quickly. We have the original function, the blue line, which is not convex. It is not convex, not concave even. So we compute the tangent majorant of this function, which is a function which is tangent to the original one, and it is greater or equal than the original one. In this 2D example, we have this red point, the tangent point, where from which we compute the tangent majorant to the original function, and this majorant is depicted in yellow. We minimize this majorant, which is convex, so it is easy to, or at least is less difficult to minimize. We find this green point in the yellow line. We consider the relative point in the original function, okay? And then we'll start the procedure again. From this green point, we compute another convex tangent majorant of the function. We minimize this new yellow function, and we proceed until convergence. Indeed, there are under suitable hypotheses, this method converges to the true solution, to the minimizer of the original function. Okay. How did we proceed to compute this tangent majorant in our problem? We just computed the linear approximation of the concave term, okay, just using mathematical tools from matrix calculus. So we have at each step of the MM approach to minimize f plus this trace term plus the regularization function. And this trace term looks like this formula, which involves the previous step of the MM approach and the covariance matrix and the noise level sigma. We can observe that F is convex and spectral because we proved it in the original work. G0, which is selected as a convex and spectral regularization function, leads us to have F plus G0 convex and spectral. This trace term is a linear term, luckily. We can select G1 belonging to gamma 0. Then the solution to each step of the MM approach can be computed by the Douglas-Rushford approach that we've seen so far. Okay, so we have everything at disposal to solve this non-convex problem. To validate this approach, we generated firstly sparse precision matrix. Here I present just one example. We generate a sparse precision matrix with dimension n by n equal to 100. We compute the inverse of this precision matrix, which is used as the covariance matrix of a Gaussian multivalued random variable. We generated 1000 realization of this variable. We added Gaussian noise of variance sigma squared, leading us to have the true covariance matrix, where it is the pointer here. We can compute the empirical covariance matrix from this excess, which follows the very well-known formula. And to validate our approach, we used three different types of measurements. The first one is the false positive rate, which counts the number of wrongly added elements to the solution. So non-zero elements on the solution which are not present in the ground truth. The true positive rate, it is the fraction of the correctly found elements on the matrix. And the last one, the relative mean square error, is just error on the original covariance matrix, okay? Then here I show you just a slide which represents the results for the noise level sigma equal to 0.5. We selected as G0 the spectral function, the Schatten inverse norm, where P is equal to 1. And G1 is the L1 component-wise norm. I don't know if you can see on your screens, but on the left, you have the true covariance matrix. In the middle, the empirical covariance matrix. So you should see that is quite noisy. And there are some elements that are not present in the original one. And on your right, the sigma rec is the reconstruction of the covariance matrix. For this instance of the noise level, we have a relative error of 0.12, more or less, a false positive rate of around 2.6%, so quite low. So it means that we add a very small number of non-zero elements that are not present in the original solution, and a true positive rate of 100%, which means that we can recover all the non-zero elements on the ground truth. Moreover, we compared our MM approach with the Douglas-Rushford approach and with the G-Lasso approach. What do I mean with this? It means that we generated several instances of synthetic data at different noise level from 0.1 to 0.8. We solved these instances with our MM approach, the blue line. So remember that when we use this MM approach, it means that we are including information about the noise in the model. On the other hand, we tried to solve it using the same regularization function with the Douglas-Rushford approach, where the noise information is not included in the functional. Finally, the yellow curve represents the performance of the classical G-Lasso approach, where we solve the problem just using minus log det plus the trace term plus the L1 norm. You can see that as the noise level increases, G-Lasso approach tends to have a very high false positive rate. It means that it adds a lot of elements that are not present on the original matrix. On the other hand, Douglas-Rashford and our approach seems to give a more reliable result, but the approach, and so the functional which includes the noise information inside the functional, is very, very robust with respect to the noise level. Indeed, as the noise increases, the false positive rate stays below around 0.4. While for high noise level, even the Douglas-Rashford approach starts to increase the number of falsely added elements on the matrix. This behavior is also very evident with respect of the relative mean square error. Indeed, approach stays quite low as the noise increases. You can see the blue curve. The Douglas-Rashford again is below the performance of the approach, while the classical G-Lasso fails to recover correctly the covariance matrix. These are experiments done on synthetic data, so we moved on to on a real-world data set. This dataset is included in the Archipel Molen project, which collects some weather information from 55 weather stations situated in the Molen region of France. These data are about rain, precipitation, the temperature, the wind, and some other data. You can see in this slide a couple of snapshots of this dataset. In this dataset, there are hourly information for the period of time from the 1st of January to the 31st of January 2014. And so we decided to focus on wind information, mainly on the speed of the wind and on the direction. We collected this information in two matrices, WS and WD, from 30 stations and for just 3 consecutive days. You may wonder why we selected just 30 stations. There are two main reasons. First one was just to reduce the data. And moreover, there are several stations that has incomplete data or unreliable data, because sometimes there are zero values or even values that are completely outliers that have no physical meaning. So we discarded these stations. And moreover, we selected a time stamp of 3 days, just because in 1 month, the behavior of the weather can be very, very different from, for example, in 10 days. So we concentrated only on a small amount of time to see what happens in that timestamp. So we use this information for WS and WD. We construct this matrix, WDS, which is the Hadamard product of these two information matrix, because we want to couple the direction and the speed of the wind. We employed this matrix in our model, where I recall the formulation, where S is this matrix where given by the Hadamard product of D and S1, where S1 is just the covariance matrix given by this WDS, and D takes into account the relative distances between the weather stations. Finally, sigma, used as the noise level, is the standard deviations of the elements in the matrix WDS. We run our algorithm on this problem, and then we obtain this graph represented on a map. You can see that mainly three subgraphs arise from this solution. One is on the west part of this coast, which suggests that there are some interlacing between these locations. There is another cluster on the east part of the map. And finally, in the north, we have five nodes that interact with themselves. This seems quite reasonable because we know that wind affects mainly coast, and in the mainland, maybe there are not so much interaction. So our approach seems to give a very reasonable physical solution. Of course, we tried to solve this problem with the G-Lasso approach and the Douglas-Rushforth approach. I present this for comparison. This is the graph given by the Douglas-Rushforth approach, which is mainly quite a complete graph, not so complete, but it seems to find all the nearest neighbors to each node. So it is not so, it doesn't give so much information. And with the G-Lasso approach is not completely reliable. Then finally, let me sum up what we have done in our work. We provided proximity operators for several spectral functions, namely Frobenius norm, log det, and von Neumann entropy coupled with regularization functionals. We developed a non-convex formulation for solving matrix optimization problems, problems which are in the context of noisy G-Lasso. And we developed also a novel approach to solve such problems. The numerical experiments that are present in our original paper shows that the performance of our method outperforms the state-of-the-art methods. And moreover, we are moving to extend our results to complex Hermitian matrices and also to non-squared matrices using the singular value decomposition instead of the eigen decomposition. And we are working also on models that take into account also the matrix A that appeared in the context of relevant vector machines. If you want to deepen the results about this work, you can, of course, write me an email and ask for information. And you can retrieve also all the theory, the proof of the theorems, and so on in two papers, actually one paper here on Signal Processing Journal, and on one proceeding at the IEEE ICASP 2018. And if you want to play with the code that I wrote in MATLAB, you can find it in my website. And then thank you very much for the attention, and I'll be ready for any question that you have.
Thanks, Alessandro, for your interesting talk. We have enough time for questions, so please.
I have a question. Thank you so much. I really enjoyed your talk, Alessandro. Maybe this is more like a curiosity than a question. If you can go back to your set of hypotheses for the inverse covariance set of hypotheses, like what you're assuming on your...
Here?
Okay, so yes, so basically you're assuming like a Gaussian distribution both for the noise and for the data, right?
Yes, yes.
And also the distribution on the noise, basically the noise covariance matrix is a scaled identity.
Yeah.
So I would like, I mean, if you have any insight about how easy it could be to generalize these hypotheses, to non-white and Gaussian noise, or also to different distribution. I mean, how important is to have to deal with the Gaussian distribution here?
Actually, you mean, if I understood well, you mean let me go maybe from here, maybe.
Yeah.
Okay.
Yes. Yes.
Actually, we've seen that the most part of the literature for now deals with Gaussian noise. And moreover, indeed, this S's comes from Gaussian realization with a covariance matrix, which is a scaled identity.
Yeah.
We were starting to consider also non-scaled identity covariance matrices. Actually, it's part of the current work we are studying just now. But for the generalization of different kind of noise, I'm not aware of any results or if there are anyone that is studying about this actually.
Okay. Well, it's already interesting that you can generalize to non-white noise.
Yeah, yeah, so you're right. You're right.
This could really be great.
Yeah,
okay.
yeah.
Thank you.
Indeed, we are working also on exactly this formulation, which it takes into account also in the functional, the matrix A.
Okay.
Okay.
Okay. Okay. Thank you.
Thanks.
Any other question? Let me check in the list of participants if someone raised his hand. No? Well, actually, I have a curiosity on the experiment that you made on real data.
On real data?
On real data, yes. I'm not an expert on graph theory, so I just want to better understand what do you mean when you say that the nodes interact each other? What is the core information, I mean?
Yes. In this case, when I say that nodes interacts one with each other, it means that there is an edge connecting the node. For example, let's see in this slide, we can see that these three nodes, 13, 16, and 25, which represents the weather station listed here, there are some interdependence within these nodes. They are connected. Okay. So meaning that they talk to each other means that there is an edge connecting the two nodes. Okay. For example, 13 and 7 are not interacting because you see that there are no edges between the two. Okay. These edges are represented in the matrix form with the adjacencies matrix. Okay. It's a symmetric matrix where the element ij is different from 0 if and only if the node I and the node j interact with each other.
Okay, so then you basically extract the information that you need for each case, each phenomenon?
Yes, exactly. In this case, you can interpret this one as which region in this map influences other region. For example, you can say that here in the eastern part, these regions depends one of each other because the wind influences the speed and the wind in other part of the map.
Okay.
Okay.
Okay. That's clear.
So indeed, if you think about the wind hitting the southern coast, is not so meaningful that this wind influence the wind on the northern coast because we are all the mainland between the two coasts. So, like in this case, it's quite strange that you have such a complete graph. Okay. I know that this interpretation maybe requires also weather experts, but depends on the data set, on the application and so on.
Okay, thank you. If there are no other questions, let me thank again Alessandro for sharing his research with all of us.
It was a pleasure for me.
And let me thank also all the audience for being here. And we will see for the next PRIMO talks in a couple of weeks. Thanks again.
Bye-bye, thanks.